Okay, brilliant. Well, thank you, Yang Yang. Thank you very much for that introduction. It's great to be here virtually. It'd be nice to be there in person, of course, but yeah, hopefully we'll be back to normal soon enough. As Yang Yang said, I am largely interested in kind of the intersection between data-driven approaches to optimization and control. But today I'll mostly be focusing on something that's squarely in the bounds of optimization. So yeah, unfortunately, there's nothing to do with imaging and almost nothing to do with data, but at least I classify it with the optimization category. This work is joint work with some fantastic colleagues and collaborators of mine. Most of the good ideas here are theirs, and most of the hard work as well. I'll largely be presenting results from a paper that can be found on arXiv. It goes without saying that many problems in practice often combine discrete and continuous decisions. These arise. Sorry. Yeah. Okay, 1 second. Sorry about the interruption.
No problem.
Problems that combine continuous and discrete decisions arise in a lot of application domains, but for our group, we're mostly interested and motivated by problems that come from planning and control in robotics. So a classic example is seen here that showed up during the DARPA Robotics Challenge, of which MIT was one of the participating teams. So here we have a robot that's trying to navigate some rough terrain, and we see that there are some higher level discrete decisions that need to be made, such as where the robot should step. Should it go kind of left or right around these various obstacles or foot positions, as well as, of course, lower level continuous decisions that should be made, such as how much torque should one apply to the various joints and actuators in order to carry out the motion and stabilize the robot. We see a similar blending of high-level discrete decisions and low-level discrete continuous decisions, rather, in many other problems in robotics. For instance, quad-rotor navigation, you have the high-level discrete decisions of whether you should go, say, left or right around an obstacle like a tree, as well as lower-level decisions such as what velocity and acceleration should you take when you follow this path, which is closely related to how much torque you should apply, which might be influenced by how much energy you can afford to consume. Similarly, in robotic manipulation, which is an area of increasing interest in our group, you have other kind of discrete decisions, such as how to avoid obstacles, not only in the kind of three-dimensional space, but also in the configuration space of the robot, which can actually be much higher dimensional. For instance, these robots each have 7 degrees of freedom. These collision constraints can be quite complicated because of the possibility of self-collisions between the robot, especially if there are two arms involved. So you might say that, obviously, this is an interesting problem, but haven't we made a lot of progress towards solving this? After all, quite periodically, Boston Dynamics releases spectacular and extremely impressive videos of robots seemingly making these great decisions that are blending discrete and continuous decision variables. And it's absolutely true that these are extremely impressive demos, and robots are very capable these days. But we can gain some more insight if we dig a little bit deeper into how these kind of demos are constructed. So according to Boston Dynamics themselves, the planning for this Atlas humanoid robot really consists of kind of 2 phases. There's an offline stage in which you pre-compute a library of template behaviors, such as hopping and jumping and maybe even running or dance moves increasingly these days. And then there's an online phase, which they refer to as trajectory morphing or behavior blending. This is more of a continuous optimization stage, often involving something like MPC, which allows these template behaviors to be varied slightly. Perhaps there's a slight difference in the position or even shape of the box compared to what you expected, and you can adjust for that slightly by kind of continuously adapting your pre-planned behavior. However, these sequences of behaviors, the sequences of templates that the robot is following, for instance, whether I should hop onto this box, whether I should place my foot here or there, this is hand designed. Specifically, there really is a person who designs this sequence of moves that the robot is going to perform. As a result, there's not a lot of scope for the robot to react to structural changes in the environment. For instance, if there is a new box that was unexpected, or perhaps a large disturbance arises and it needs to completely deviate away and perform a different kind of move than it was expecting. And indeed, Boston Dynamics has hinted that this task of kind of choosing the sequence of moves, these high-level discrete decisions, really could be a job for a planner. So that's a big part of the motivation for today. We're interested in these kind of problems that blend discrete or combinatorial decisions with continuous decisions. These problems are quite interesting and challenging. They also show up in a lot of application domains, certainly in robotics, but also in other areas such as power systems. The problems we're interested in are kind of moderately high dimensional, tens to maybe tens of thousands of variables. So not insanely large, not massive problems with millions of variables like you might find in scheduling or logistics or something like this. So with that kind of background, the goal for today is to present and come up with an optimization-friendly abstraction that captures the essence of these problems, this blending of discrete and continuous decision-making. In particular, by optimization-friendly, I mean something that we can solve quite efficiently, certainly fast enough to be done in the domain of kind of replanning, that is on the order of kind of hertz or even faster, certainly faster than kind of minutes or hours. And of course, the sub-goal for today is to also try and improve on the state of the art in this area. Okay, so our attempt at such an abstraction that captures this can be basically summed up with this picture. So we kind of start with the shortest path problem, the classic discrete optimization problem as inspiration. And we introduce or propose what we call the shortest path through graphs of convex sets problem. So we can really kind of summarize it with this picture. As opposed to just having discrete decisions, which is which vertex do you move to, you now have continuous decisions, which is where do you decide to move to within a set that is associated with each vertex. And similarly, instead of having fixed costs per edge that you might travel, the costs can now be intricate functions or continuous convex functions of these continuous decision variables. So this is quite a flexible and powerful problem formulation. As we'll see, we can model lots of interesting problems with this framework. It also gracefully blends these discrete decisions, such as whether we go left or right around an obstacle or use the left foot or right foot of a robot, etc., with the continuous decisions where you are in the convex set, which are related to force and time and fuel consumption and cost and these lower level factors and considerations. And it's also efficiently solvable, at least for many of the problems in application areas that we're interested in. For instance, or I should say rather that the price that we pay for this flexibility is that the problem is NP hard. However, we will present a mixed integer formulation of the problem that can still be solved relatively efficiently due to its quite tight convex relaxation. Okay, so the outline for the rest of the presentation is as follows. We'll formally introduce this graphs of convex sets framework, including describing how it can be applied to model some of these problems of interest. Then we'll move on to talk about the solution approach, that is, how do we construct this good convex relaxation that results in a pretty strong mixed integer formulation of the problem. Then I'll present some numerical results and implementation on actual hardware, and then we'll wrap up later. Okay, so the graphs of convex sets framework. So as I mentioned, the starting point is a directed graph, as usual, has vertices and edges. And this is, we can really think of this as encoding or modeling the discrete decisions that we're going to have to make. We add to this graph at each vertex a convex set, x sub v, which we will assume to be compact. And we also add a continuously varying decision variable x, which is constrained to live in this convex set. Again, one decision variable per convex set and one convex set per vertex. For each edge, unlike the classical shortest path problem, where the edge cost is just a fixed non-negative scalar, now for each edge from vertex u to vertex v, we will assign a convex kind of length function. So this is a function whose domain is the convex set associated with the vertices that it links, here xu and xv, and it maps to the extended reals, the non-negative extended reals. So in particular, we want the extended reals so that the domain of this function can encode constraints on xu and xv jointly. So the usual kind of thing, if you have certain constraints that your continuous variables have to satisfy, you can put them into the cost function with an indicator or something like that. We have the notion of a path, which is the usual familiar notion. It's a sequence of distinct vertices that is beginning at some distinguished starting vertex and terminating at some target vertex, which we can think of as our start and our goal, respectively. And of course, every vertex has to be linked by an edge that actually lives in the graph. Okay, so to wrap all that up, the shortest path problem in graphs of convex sets can be defined as follows. We need to search for a path, P, such that for every vertex along the path, we find a continuous variable x that is constrained to live in its corresponding convex set. And we want to find such a path and such continuous variables such that the sum of these convex costs along the path is minimized. So just to be clear, we're going to optimize over both the paths, the discrete decisions, and the vertex locations, the continuous decisions jointly. So yeah, if there are any questions about the problem formulation, don't hesitate to ask, but let me give a few illustrative examples of how we can encode and model some of our problems of interest with this framework. Hopefully we'll clear some things up too. So as a first example, let's consider constrained regulation of a linear dynamical system. So our goal is to, over some fixed time horizon, capital T, minimize the convex cost of the state and action of a dynamical system that evolves with these linear dynamics. The state at time t plus 1 is just a linear function of the current state and control action. But the state and action are constrained to lie in some convex set. These could represent limits on your actuators and safety constraints on the state. There's some given starting state, and we'll just assume, more or less without loss of generality, that we're trying to drive the state to the origin. So we can encode this as a shortest path problem as follows. For the edge lengths, we have these convex functions here that are the costs associated with the state and the action. The convex sets in our graph will be the set of the constraint set for the state and the action. So to the variables, the continuous variables that must live in these convex sets will be the states and the actions at each time, respectively. Each time will correspond to a particular vertex. And also recall that with the domain of the cost function can also encode constraints. And so we will use that property to encode the dynamics as the edge constraints. The constraint that the states must satisfy the dynamics can be encoded into this edge length function here. Also note that in this case, the graph and the notion of path is quite trivial. There's really only one path from the starting vertex to the target vertex. There's no deviations that we can make. Time will just increment from time 0 to time 1 all the way to the final time here. So this is really just an illustrative example. There's no interesting discrete decisions to be made here. As a slightly more interesting example, we can consider the minimum time constrained linear regulation problem. So everything is more or less the same as before. We still have linear dynamics. We still have convex constraints on the state and the action. But now our goal is to minimize the time in which we drive the system state to the origin. So now we have a similar shortest path problem, but the underlying graph looks a little bit different, a little bit more interesting. So again, we still have a vertex corresponding to each time. We need to pick some kind of upper bound on the time that we're willing to consider. In this particular figure, it's 4. But instead of only having edges that progress from time 1 to time 2 to time 3, etc., we also have the option at any time to potentially jump to the end, to jump to the final state, because we're trying to minimize the time. So maybe it's possible that we can drive the state all the way to the origin in one time step. We might incur a lot of costs, but that might be possible, in which case that would be the optimal solution. So the only real difference here is the underlying structure of the graph and the fact that now the edge lengths are just equal to 1, because that's our notion of cost. We just want to minimize the number of time steps it takes to get to the origin, so we minimize the number of transitions or number of edges that it takes in our path. Okay, we can also have even more interesting examples where we might want to do a similar kind of regulation problem, but over a disjunctive domain. So again, it's quite similar to the first problem. We have convex costs in linear dynamics, but now instead of a convex constraints on our state and action, we have the union of two convex sets. Now we can represent this as a shortest path problem in graph of convex sets. And here, once again, we have to change the graph. So now, instead of just having a vertex more or less corresponding to each time, we now have two vertices for each time, one corresponding to each possible mode, if you like, each possible convex set that the state and action could be living in. So at each time, we can either choose to transition to, say, set D1, or at the next time step, we can choose to transition via this edge to set D2. So we see that our convex sets are now a little bit richer, and so is our graph. And so more broadly, for these kind of optimal control problems, the graph really encodes the underlying spatial temporal structure of the space of solutions that we want to consider. The spatial structure can include different modes that we might want to live in, might want the state and the action to live in. So this can encode things like hybrid model predictive control. And also the temporal aspects can include things like minimum time, as we saw earlier. Okay, so that's some of the control applications. Another big application.
Can I have a question here?
Yeah, absolutely.
Yeah, I'm trying to relate your example to your the general formula in the beginning. You have the constraint on this pass.
Right.
You have, I think, the minimum or maximum about this pass. How that pass relate to, like, the examples here? Which one model the pass?
Right. Yep, that's a good question. So yeah, maybe we can go to this minimum time problem, and so we can think of each one of these sets here as containing the state and the action at a particular time, and then the path that we can take is to either simply advance to a new state and a new action, which will lie in this set at the next particular time. Or we can think of taking a path that goes directly from our initial state directly to the origin in a single time step. And so this way, the path is really the kind of discrete decisions in this graph. You can kind of move to another set up to 4 times, or you can move directly to the origin. And the path is really encoding how many time steps you choose to take to get to the origin.
Okay, so can I understand, like in the example, the path is something represent your constraints? It's like initial is you are somewhere and finally you get to your target point, right? And but the path will subject to these constraints, and the length, you don't have the length of the, at least for this example, you don't have the constraint on the length of the path.
Right. So, yep, that's a good question. So in this case, we only want to minimize the time it takes to get to the origin. So we're only interested in kind of the number of transitions. So in this sense, the edge length is just equal to 1, which is to say that if you choose to make a transition, you incur a cost of 1. But we also have, in some sense, in the domain of the edge function, we have these constraints that represent the dynamics. So, of course, the optimal solution, if possible, would be to transition straight to the origin in one time step. But because of the dynamics, it may not be possible to do that. In particular, because the action is constrained to live in this set. For instance, you might not be able to choose an action that's large enough to drive you to the origin in one time step. So you might need to, by respecting these edge constraints, you might need to take multiple time steps, multiple edges before you can reach the origin.
Okay, so in that sense, in your general formula, the path, that constraint set is not a fixed set, is it? Or it just satisfies some things?
So there's this.
Yeah, if you go to this formula, you have this capital P. Is that a fixed set or?
Right. Good question. Yeah, so this is it is a fixed set. This is kind of the set of valid paths. So any path that only visits a vertex once and moves along an edge, a valid edge in the graph, that's considered to be a valid path. So for instance, you can't move from here to here directly. The edge is going in the wrong direction. But in this particular example, the path takes this edge, then this edge, and then this edge. So any any valid ST path, any valid path from source to target is in P. That's fixed for all the problems.
Okay, so for this example, like you add some vertex, you next step you must move to another vertex. You cannot say stay in that region.
Okay, yeah, that's a very good question. Yeah, so here for these optimal control problems, that's why we kind of have this. We kind of duplicate this set multiple times, once for each time step. So, you would like to, in some sense, you just want to stay in this set for all time. The state and the action must lie in this set D. But in order to fit our framework, we introduce duplicates.
Oh, I see. Okay. Yeah. I see.
For each time, yeah. No, thank you. That's a very helpful question.
Thank you.
Yeah. Okay, so. Probably an even simpler, I hope, example of or another problem that can be encoded in this graphs of convex sets framework is the problem of collision-free motion planning. So here's a simple kind of cartoon in the 2D plane, but in general, this collision avoidance problem can be much higher dimensions. So our goal here is to connect some initial configuration to some target configuration via some piecewise linear path that is going to avoid these obstacles. So that is the path is not going to intersect with these red obstacles here. So the approach or how we would frame this in the graph of convex sets framework is to first decompose the collision-free space, that's all the space that is not inside the obstacles, into a union of convex sets. So an example is given down here with these collision-free convex sets shown in green. For today's talk, I'll just assume that this decomposition is given to you, and there's some really great work by some colleagues in the lab to find such decompositions. You can check out the following paper, but this kind of remains an interesting open problem, and we'll just assume that for now you're given this decomposition of the free space. So once you have this decomposition, you can construct an adjacency graph, a graph that has a vertex for each set here, and an edge between the vertices as long as the two vertices intersect. So for instance, here between 2 and 3, these sets intersect along the boundary, meaning that it's possible to move between 2 and 3 without intersecting, colliding with an obstacle. So hence there's an edge in the graph between 2 and 3. Next, we can assign a line segment to each region. So this is really the continuous variables in our convex set that we're going to search over. So for example, if we look down here at region 1, we see that our continuous decision variable x really has 4 components. It has the x and y coordinate of the starting position of the line and the x and y coordinate of the ending position of the line segment. And the convex set, of course, now is the product, the Cartesian product of this two-dimensional convex set. By constraining the start of the line segment as well as the end point of the line segment to be in the region, we of course can constrain the whole line segment to be in the region. So this is how we ensure that the paths remain collision free. Then of course we need the path to be continuous, and so this can be enforced as an edge constraint. So specifically, we just need to have a linear equality constraint. Again, we can build these kind of edge constraints into the domain of the edge cost function. And these are just linear equality constraints that say that the end coordinates of, say, for this one, the x1 have to match the starting coordinates of x2 to ensure continuity. Then, if we would like to find the shortest path, the minimum piecewise, the path of minimum length from source to target, then we can use a vertex cost that just encodes this length segment. So for instance, again, if we look at the edge from 1 to 2, we're just interested in this length of this line segment here, which is a simple convex cost on the decision variables associated with this set. It's also worth mentioning that we can extend this basic approach to polynomial paths, not just piecewise linear paths, by using Bezier curves. So again, the issue of how do we make sure that the path, the continuous path, remains in the collision-free region is taken care of by using this convex hull property of Bezier curves. So as long as the control points of the Bezier curve live in this convex set, then the entire Bezier curve will also lie in this convex region as well. Although this is a conservative condition, the converse is not true. We can't parameterize all paths that live in this set by this strategy. We can also have a much more kind of interesting, or I should rather say that we can also parameterize the time that it takes to traverse this path. So instead of just having a kind of geometric path through the configuration space, we can also parameterize how long it takes to traverse it. And this allows us to really search over trajectories, meaning that we can also, via the edge length costs, put constraints as well as costs on things like the trajectory duration and search for minimum time paths. We can impose velocity constraints. We can put penalties on higher order derivatives like acceleration, and impose continuity of the derivatives as well. Okay, so yeah, as I mentioned, it's quite a flexible problem framework, and the price that we pay for this flexibility is that the problem is NP hard. So it's not too hard to see. We can start off by observing that if we were to fix either the path P or the continuous variables X, then the problem would be easy. For instance, if you fix the continuous variables, then these edge length functions are now just constant because X or the continuous variables X are constant. So now we just have a classic shortest path problem where we're only need to make the discrete decisions of which edges to take. Similarly, if we were to fix the discrete decisions, that is, we were to fix which edges we're going to take through the graph, then we would only have a continuous convex optimization problem over the continuous variables xb. So this is just minimizing the sum of convex functions subject to convex constraints. So again, depending on how these functions and constraints were represented, this is another relatively easy convex optimization problem. However, if we decide to search for both simultaneously, the problem is NP hard. And I might move through this relatively quickly, but this is kind of easily seen with an example. So for instance, suppose we consider this graph here with these convex sets. There are 4 vertices, and our edge length functions are given by the square of the 2 norm. So yeah, just the distance between these 2 points squared. Because of this 2 norm squared, the optimal solution will prefer to evenly space out these continuous decision points. Roughly speaking, because of the 2 norm squared, it's cheaper to take 2 medium-sized steps than to take 1 big step and 1 small step. So as these sets become larger and larger, we'll see that the optimal thing to do, when the sets become so large that you can basically put your continuous decision variable anywhere you want, the optimal thing to do will be to line up all your continuous decision variables in a straight line, equally spaced from the source to the target. And now the question, or now the reality is that the more vertices you can visit, the more steps you can take to reach that. And because of, once again, because of the square in the 2 norm, the lower the cost will be. So really, in some sense, the question now becomes, is there a path that visits every vertex in the graph? That way I can have as many steps as possible to reach the source and the target. And you can see that this is essentially equivalent to the Hamiltonian path problem, which is, can you find a path that visits every vertex in the graph? And this is one of Karp's classic 21 NP complete problems, which is reducible to GCS in polynomial time, therefore implying that this graph of convex sets problem is NP hard. Okay, so that kind of tempers, I suppose, our expectations about how easy it's going to be to solve this problem. So we'll need to do something careful if we hope to solve these problems efficiently, and that's what we'll present next, our solution approach based on convex relaxation, and which will lead to a pretty strong mixed integer formulation of the problem. Okay, so our goal here, or what we will present, is a fairly compact mixed integer convex program. By compact, I mean that we're searching for a good balance between the size, which is roughly the number of constraints and decision variables, and the strength of the program, which is how good is the convex relaxation. It turns out that for many of our applications, the convex relaxation is often very tight, sometimes even exact. And when the relaxation is not exact, we can often recover very good solutions by a kind of randomized rounding strategy that I'll talk about, or we can resort to a branch and bound algorithm if we really want to certify that we have the optimal solution. So there are three key steps to constructing this mixed integer formulation of the problem. I'll just briefly sketch them out, and then I'll go through them in detail. So the first is to start with the integer programming formulation of the classical shortest path problem. So we parameterize our paths with these kind of flow variables that that either take on 0 or 1 to denote whether the path takes a particular edge or not, and linear constraints to essentially enforce conservation of flow to make sure that we do in fact have a valid path from the source to the target. We will use the linear programming relaxation of this problem, which will relax these flow variables to instead be continuous on the interval from 0 to 1 instead of discrete. We'll see that this LP formulation of the classical shortest problem extends fairly naturally to our graph of convex sets problem. However, this natural generalization results in a bilinear program. Specifically, we end up with these products of the flow variables and our continuous decision variables that live in these convex sets. So this is essentially a mixed integer nonlinear program, and not particularly nice to solve. We'll obtain a mixed integer convex program via a convex relaxation of these bilinearities using the notion of a perspective of a set. Here's a kind of cartoon representation, but it will become much clearer later what I mean by this. And this relaxation turns out to be exact whenever you're at the extreme points, or whenever you're at these integer feasible solutions, these proper flows through the graph, which implies that this mixed integer formulation is valid. In other words, in some sense, this is what allows us to do branch and bound on the problem. Okay. So yeah, step one, this is the linear programming formulation of the classical shortest path problem. Hopefully this is relatively familiar, so I'll go through it kind of quickly. So we have, in the classical problem, the edge costs are constant. They're just non-negative scalars that give you the cost of traversing a particular edge. As I mentioned, we would parameterize the paths with these flow variables. In the integer programming formulation, there'll be binary variables, 0 or 1, that say whether or not you take a particular edge. But in the linear program, of course, we relax them to be continuous on the interval from 0 to 1. Then we have these constraints that ensure that we have a valid path. At least they would ensure that we have a valid path if the flows were binary. When we relax them in the linear programming formulation, it gives you the convex hull of all of the possible paths or the possible flows, at least through a given vertex. So I say this just to emphasize that what we have at each vertex is what's called the local flow polytope, and it's just a collection of constraints. In particular, if we look at an example of a vertex here, we can see all of the incoming edges and outgoing edges. With some abusive notation, we can use y of v to group together all of the flows that happen to be incident to this particular vertex. And then the constraints that comprise this local flow polytope, the constraints that the flows are non-negative, that the flow through a vertex is conserved, that is, the sum of the incoming flows has to be equal to the sum of the outgoing flows. And also a degree constraint, which is that the total flow through a vertex should be less than 1. This is not strictly necessary for the classical formulation of the shortest path problem, but it will be useful for the generalization. So we keep this somewhat redundant constraint around. And this will give rise to the minimum cost flow formulation of the shortest path problem, where we're trying to minimize the product of the flows and these costs. So minimize the cost of the flow, subject to these essentially conservation of flow constraints that are enforced at each vertex. Okay, so if we start with this classic LP formulation of the shortest path problem, we can see that there's a fairly natural extension to graphs of convex sets. So instead of having now constant edge costs, which are just non-negative scalars, we can replace them with these functions of our continuous decision variables, which represent the cost of taking a particular edge. And of course, we can also add the constraints that these continuous variables have to live in their convex sets as well. Now, this is a kind of natural generalization or extension, but has some slight technical issues with it. Specifically, this product here, if you recall, these functions can take on infinite values. They take on values in the extended reals. And this product between flow and the function may not be well defined if the flow is 0 and the function is infinite. So to kind of get around this slight kind of technicality, we will introduce some auxiliary variables, one for each vertex, one for each edge, sorry, z and z prime. So in particular, we'll make this change of variables such that the product of the flow and the spatial variable u for a particular edge going from u to v is now given by z of e. And for that same edge, the product of the flow and the kind of the spatial variable at the arriving vertex v is given by z prime. So we can see that with this simple change of variables, we can replace x of u with z of e divided by y of e and just plug it into the objective here. So it's a kind of change of variables in the cost function along with these corresponding constraints, these bilinear constraints that are really defining these new variables z, e, and z prime. So it doesn't look like we've done too much just yet, except possibly divide by 0. But this cost function turns out to be quite a useful object. In particular, this cost function here is recognized to be the perspective function of our original cost L of e. So you can have in mind the original function L of x u and x v, and this perspective operation creates a new convex function in terms of the variables y, z, and z prime. So this is somewhat nice, but the real reason that we do this is that it behaves appropriately when y takes on values equal to 0. So roughly speaking, when y goes to 0, we essentially want to turn off this cost. We want to say that our flow is not taking this particular edge in the path, and so we should set this cost to 0. And this is exactly what this perspective function achieves. So because these convex sets xb are compact, we know that xb will also always take on a finite value, or will always be bounded. So when y goes to 0, it implies that z and z prime also go to 0, which means that the perspective function will always take on the appropriate value of 0. So in some sense, we're just handling this turning on and turning off of the costs appropriately. Of course, we haven't really done anything. We haven't really made the problem easier. Maybe the cost is now convex, but we have pushed all of the nonlinearities and non-convexities into the constraints. So these problems, in some sense, are completely equivalent. We've just kind of pushed the problem into the constraints instead of the objective. Okay, so the next step is really just a change of notation. We'll kind of compress the notation to make it more transparent what we're doing in our convex relaxation. So in particular, we're just going to start to group the variables in our problem in a vertex by vertex way. So again, we can look at a typical vertex here. Again, all of the flows that happen to be incident to this vertex, we can group them into this variable y of v, and recall that they have to live in the flow polytope, which is basically encoding conservation of flow. Then we can look at the continuous or the spatial variables x. There's of course one x v associated with each vertex, and it has to live in its corresponding convex set. Then we can take a look at these new variables that we've just introduced. So for all the incoming edges to this particular vertex, we have this product of the flow and the variable at that vertex, which we called z prime for this particular edge, all the incoming edges. And for any outgoing edges, we have this, again, the product of the flow variable, and the spatial variable was denoted z. So we can simply group all of these new z variables together into a single matrix variable. In particular, if we were to take the product of the spatial variable and this vector of flow variables, we would expand it out and get these terms. And by making the substitution and grouping them all together, we just get this matrix variable z. So yeah, I can't stress enough that this is just a change of notation that will make it easier to express the relaxation that's coming up next. So with this change of notation, we can define this set. One such set can be defined for every vertex. It has the spatial variable, the flow variable, and this new matrix variable. The flows must be constrained to the flow polytope. The spatial variables have to live in their convex set, and the matrix variable has to satisfy this bilinearity. So maybe it's helpful at this point just to recall that this was our problem that we arrived at with the change of variables. We have these nasty bilinearities here, and all we've done by introducing this new notation is compress our notation, and we can write that same program equivalently as follows. Again, we're trying to minimize this perspective function of the cost, which allows us to turn on and off the cost appropriately, depending on whether the flow goes to 0 or not. And then all of the other constraints in the problem are kind of grouped vertex by vertex into this set here. Again, just to emphasize, including the kind of problematic constraint, which is this bilinearities here. Okay, so hopefully that's relatively clear. And step 3 of the relaxation of the mixed integer formulation is to actually present the relaxation of these bilinearities. So at this point, the kind of fruits of our labor for introducing this new notation is that we can work at a little bit of higher level of generality. So recall that we have this set. We have some convex set, another convex set, which was our flow polytope, and these nasty bilinearities. And our goal now is to find some kind of good outer approximation, which I'll call S prime, for this set. So we can kind of visualize this over here. Y lives in a convex set, so does X, and here is this nasty set, non-convex set up here due to the non-convex bilinearity. So our main result is really a very simple kind of lifting of valid inequalities. So in particular, suppose that we have a valid inequality for the set Y, that is to say, some affine function that is non-negative whenever Y happens to live in this green set here. Then we can construct a new inequality here, rather a new constraint here that will be valid for the original non-convex set S. So that is to say, we found a way to lift, in some sense, a valid inequality for Y to construct a valid constraint for the original set. And by grouping together many of these valid constraints, we can construct our outer approximation of this non-convex set S. So at first, this particular expression might look a little bit, it's a bit complicated or cumbersome, but it's really a very simple idea. The idea is that because X lives in this particular set, it has to lie in this convex set X. So therefore, if this is a valid inequality for all of the Y in this green set, we can simply multiply both sides of this inclusion by this non-negative quantity, AY plus B, to get the following valid inequality. So these two facts certainly together imply that this must be true. And then we simply make a change of variables here. We recognize that X and Y together is nothing more than our new variable Z. So with that, we introduce that change of variables, and that gives us our resulting constraint, our inclusion here. And of course, what value is this? It's not so much use to come up with more constraints for this non-convex set, unless, of course, this constraint is itself convex in the variables x, y, and z. Perhaps now we return to this perspective picture. The way to see that this is convex is that what we really have is, in some sense, the perspective of this set X. So we have that some affine function has to live in the non-negative, because it's a valid inequality, scaling of this set. So you can kind of visualize that you have the set, you introduce some new variable that's non-negative, and in the space of these new variables, you end up with this kind of perspective cone of the original set. And that's really what's going on in this constraint here. Okay, so we can imagine that by picking a bunch of valid inequalities, we can kind of create valid inequalities for this non-convex set and get an outer approximation. But the question remains, which valid inequalities should we use? Perhaps we use all of the inequalities that define the convex hull of this set, but that might be expensive. In general, it might be infinite. So how do we actually get a tractable convex approximation of this set? Well, we can recall that for this graph of...
Can I clarify something in your previous slides?
Yeah, absolutely.
Yeah, maybe previous slide. Yeah, here. So you assume like this A transpose Y plus B is non-negative. And
yes.
That's because you want to keep like the final that constraint is convex, or like in your last line you have that set, that constraint set.
Right.
So,
right.
So if I switch the sign of A and B, right, you have that is non-positive for all Y, right? And it seems like your proof still goes through, right?
So the issue is that maybe where's that figure? Yeah. So I suppose the issue is that if you have a non-positive
yes.
quantity here, it kind of flips the cone over onto the other side, and you kind of end up on the wrong side of the convex cone.
Okay. That notation means the cone, not to say something just scale this convex set. Scalar is a set. That means a cone, or
right. So yeah, it's a bit tricky, but I can hopefully clarify it. So if we were to fix lambda, or if we were to fix AY plus B, this would just be a scaled set. But lambda is allowed to vary as a variable as well, and so is Y. So in general, we kind of lift. If we were just to fix this as a positive number, this notation just means that you scale the set.
Right.
But when you consider these jointly, jointly together, they define.
Okay, then you get a cone, right?
Yeah. Okay, that's a great question. Okay. Yeah.
Got it. Thank you.
Excellent. Okay, so our question is, essentially, we can transform these valid inequalities to get valid constraints for our non-convex set, but which ones are we going to choose? Which valid inequalities are we going to choose? For this graph of convex sets problem, this Y is the flow polytope. In particular, it's polyhedral. It's defined by a finite number of these affine inequalities, as is represented in the picture here. So it's a pretty natural idea that we should just take the facets of this polyhedral, this polytope, and apply the lifting lemma to each one of the facets. And it turns out that, as you might expect, it's a very natural result that we don't lose anything. The relaxation that we would get, in other words, the intersection of all of these valid inequalities for the non-convex set would not be any tighter if we used the extra redundant constraints. To put it differently, we don't lose anything by only using this finite set of valid inequalities that define the polytope itself. So if we kind of put all this together for polyhedral Y, the final convex relaxation that we get is simply that X has to be in X. This is a convex set. Y has to be in Y, of course. And then we take essentially the intersection of these valid constraints here using the facets of the polytope. And that gives us an outer approximation of our original non-convex set S. It's an outer approximation because, of course, we drop the non-convex bilinearity. Now, a nice property of this particular relaxation is that if we were to restrict ourselves to the extreme points of the polytope, so look at any of the extreme points, for the particular case of the flow polytope, these are points where the flows actually take on their binary values, 0 or 1, then restricted to these extreme points, the convex relaxation is exact, which is to say that it agrees perfectly with the original non-convex set. The implication for optimization is that if we are to solve our problem with this convex relaxation and recover binary flow variables, then we know that actually at these particular binary flow variables, our problem formulation is exactly equivalent to the original non-convex nonlinear formulation. And so we have actually solved our problem. The cost function will take on exactly the same value. In other words, we have a kind of a valid mixed integer convex formulation of the problem. Okay, so let's see how we're going. Oops. Yeah. Can you still see the screen?
Yeah.
Okay, great. Just dropped out for a second. Yeah, I might need to speed up just a little bit to try and finish on time. So let me just quickly make some comments about relationships to other relaxations. What we have here is really kind of a set-based relaxation in the sense that we don't really require an explicit description of this set X. In particular, we might even have black box access to X. Maybe we have like an oracle that tells us if a particular point is in X, and if it's not, it gives us a separating hyperplane. And that would still be sufficient. We could still perform this relaxation. Maybe we'd have to use the ellipsoid algorithm or something to optimize with it. But we don't need an explicit functional description of the set of X. So this is much more in the spirit of these Loewe-Schreiber relaxations than, say, the relaxation linearization technique. The next thing to say is that if you do happen to have a functional description of your convex set, then the relaxation is given by the perspective function. So in particular, this question that we had before about what do these sets really look like, if you need to construct this convex cone and you happen to have a functional description of the set, then you just take the perspective of that function, and the zero sublevel set will give you this perspective cone of the original set. And finally, we assumed that this set Y was polyhedral for graph of convex sets. It was the flow polytope. If X is also polyhedral, then this construction that I talked about just reduces to the first level of this relaxation linearization technique hierarchy, if you're familiar with that. So it's only in the cases where X is non-polyhedral that you get something new and interesting, but that's often the case. Okay, so also recall that the goal was to strike a good balance between the strength and the size of the formulation. And in terms of strength, we find that this relaxation is really quite often quite tight in our particular applications in robotics. In terms of the size, it's quite compact in that it scales linearly with the number of vertices and edges in the graphs in terms of the variables and number of variables and number of constraints that we introduce. We note that we can generate additional constraints and come up with even tighter relaxations, kind of in this relaxation hierarchy style. But for our applications, this results in just more constraints and more variables, a larger problem, without much increase in the strength of the formulation. And the relaxation that I presented is also quite general and can probably be possibly be applied to some other problems of interest. But in the interest of time, I better move on quickly. Yeah, so to kind of wrap up this section on the solution algorithm, we started off with the kind of the LP formulation of the classic shortest path that can be represented here with these flow constraints for conservation of flow. And to obtain our mixed integer convex formulation of the graph of convex sets problem, we see that we added these additional constraints with this strengthening, with this lemma that I presented. So in particular, we have these extra constraints down here, which is exactly the result of applying that lemma, that lifting lemma, to the simple constraint that y is non-negative and x is in this set. So if you just multiply both sides of the inclusion, you get this valid inequality. And with the new variables, that exactly turns into these constraints down here. And similarly, we have these extra constraints here, where we have the essentially we take the conservation of flow constraints and we apply them in much the same way to this inclusion, and we end up with kind of spatial conservation of flow as another valid convex constraint. Okay, so let me just say that to recover solutions from the relaxation, sometimes the relaxation will be exact, and then recovering solutions is easy. We just look for all the edges that are equal to 1, and we know that that's our path. And then along the path, these new variables give us our original decision variables. It's very straightforward. But often the relaxation will not be exactly tight. And then there's two things that we can do. The first thing we can do is we can interpret these non-binary, so continuous flow variables as probabilities, and then sample from them. So for instance, in this particular case, we can sample transitions. We're more likely to sample this one, which will lead us to this edge, and then we can kind of renormalize these probabilities and sample again. And we can do this to sample a bunch of paths, and once the path is fixed, we can just solve for our continuous variables, which is an easy convex optimization problem, and take the best solution in the end. The other thing we can do, of course, because we have a valid mixed integer convex program, is that we can perform branch and bound if we really want to certify that we find the optimal solution. Okay, so I guess I've run a little bit of time here, but let me just go through some of the numerical results quickly. Maybe in the interest of time, I will skip over the optimal control and go through a couple of the others. So here we have an example of motion planning in a maze. This is kind of a problem that would be very easy as a discrete graph search. It would just be a kind of conventional shortest path problem. But it would be perhaps a little bit more difficult if we have kind of differential costs and constraints. So, maybe we want to put constraints on this continuous path that flows through here, constraints on velocity and acceleration. If we were to tackle this with local optimization, I think it would be quite unlikely to succeed. Sampling-based methods are quite inefficient and don't really take advantage of the structure, the underlying graph structure of the problem. And previous mixed integer approaches introduce a very large number of binary variables, in particular, a number of binaries that scales with the square of the number of cells, which in this case is on the order of millions. So if we were to, however, if we apply our graph of convex sets approach to this problem, we can consider two variants, two particular costs. The first cost is just the minimum distance, so find the shortest path through the maze from the source to the target. This is kind of like a sanity check. It should be easy, and indeed the convex relaxation is exact. But a more interesting problem is we can look for a path that takes minimum time to get through this graph with velocity and acceleration limits and penalties on the path. And in that case, the relaxation is also exact as well. You can see in particular that the paths are quite similar, but they diverge sharply at this point here, where the minimum distance path makes a very sharp turn, but the minimum time path takes a different route so as to avoid a very high acceleration penalty here. Let me just wrap up quickly with a couple of motion planning examples and acknowledge that a lot of the implementations and experiments come from my co-authors here, and also emphasize that for these problems, coming up with the actual graph of convex sets itself, the decomposition of the free space that gives you your graph and your convex sets is quite a challenging problem. And my co-authors, well, my colleagues as well, have done some great work on this. So here's an example with quadrotor navigation. We have a kind of simplified block world environment that allows us to do exact decomposition of the collision-free space into convex sets. And we test out the algorithm with 100 randomized environments. And so we're looking to plan trajectories with a cost that penalizes the path length as well as the time taken to reach the target location, with penalties on the velocity and the acceleration as well. And we find that, in short, the convex relaxation performs quite well. We solve the relaxation. As I mentioned, it's not tight in most instances, so we have to sample a bunch of paths. then it's relatively simple to solve for the continuous path once the sample path is fixed, and we can return the lowest cost solution of the 10 that we sampled. And in most of the instances, we get extremely tight. We get very close to the optimal solution to the problem. I suppose I'm almost out of time now, so I'll just make one more comparison. We can apply essentially the same idea to motion planning for robotic arms and make a comparison against some existing methods. Here's one that is using a probabilistic roadmap. It's essentially an approach that looks at a completely discrete version of the problem. So it takes your continuous free space that you can move in and finds a discrete representation of it in the form of a graph, and then does graph search. So we can see that the paths found by this method are not particularly efficient to go from one tub to another. You can kind of smooth this out by doing a kind of shortcutting method that's quite popular in practice, which improves things substantially. But we also find that our graphs of convex sets method produces very high quality paths of very short length. This is kind of backed up by the numbers that the paths are of very short length, but also the computation times online to find them are extremely competitive as well. In fact, they're even lower just than the standard graph search problem for the probabilistic roadmap. We've also tried this out in even higher dimensional spaces, 14-dimensional space with 2 7-degree of freedom arms as well. And this is a regime where the probabilistic roadmap would probably begin to struggle. So I think I've run a little bit over time by now, but I'll just give a quick plug to the Drake software package, where there's a mature implementation of this graphs of convex sets framework. So feel free to try it out for yourself on some of these demo problems, or maybe even some problems of your own. With that, I'll probably just, in the interest of time, leave this slide up. And thank you very much for your attention.
Okay, thanks a lot for the nice and very interesting